In this section, we will talk about limits at infinity. So we will examine the behavior of f of x as x approaches infinity and as x approaches negative infinity. So if r is a positive real number and c is any real number, then the limit as x approaches infinity of c over x to the r equal to 0, and limit as x approaches negative infinity of c over x to the r is also 0. Now, what does that mean? Well, basically what we're saying is that, let's say we have limit as x approaches infinity of something like 2 over x to the fifth power. Okay, now here's what's going to happen. As x gets bigger and bigger and bigger and bigger, x to the fifth, so remember, you have, let's say you have x value of like 1,000,000. You take 1,000,000 to the fifth power, you're going to get a very, very big number. So if you have limit as x approaches infinity of 2, and if I plug in x equals to a really big number, if you take 2 and you divide it by some really big number, then that's going to equal to 0, right? Like, let's say you have 2 and you divide it by this, it's going to be very, very close to 0. So that's what this is saying. If you take any constant and you divide that by a very, very big number, it's going to be approximately 0. And as x approaches infinity, then 2 divided by infinity will definitely be 0. So based on that, we are going to evaluate the following limits. And the trick here is we're going to rewrite each expression so that we have c over x to the r, where c is a constant. And the best way to do it is to divide each term by the highest power of x. Okay, so what we're going to do is we're going to divide each term by the highest power of x. So like in this example, the highest power of x is x cubed. So we're going to divide each term by an x cubed. So x squared over x cubed is x. So we have negative 31 over x. Here the x cubed over x cubed cancels out. So we have a negative 21. And then we factored it out, right? It can't just disappear. It doesn't go nowhere. Like, we have to do something with it. So we're going to factor it out. It goes to the front. So essentially what's happening is we have negative 31x squared minus 21x cubed. That's what we have. And we're factoring out an x cubed. To factor means to divide. So that's why we divide each of these terms. So negative 31x squared by x cubed, and then the negative 21x cubed also by x cubed, because to factor means to divide. So we factor it out and divide each term by that factor. So what happens here? Well, if you take negative 31 and you divide it by infinity, so a really big number, it's going to equal to 0. Now, we know that x cubed is going to be infinity because infinity raised to the third power is infinity. So if you have infinity times negative 21, we got a really big positive number times a negative number, it'll give you negative infinity. We're going to use the same principle for the second problem. We're going to factor out an x cubed. So we did that here, so it's the same thing. It's negative 31 over x minus 21. But this time, if you have a negative infinity raised to a third power, so imagine a really big number raised to the third power, it's going to give you negative infinity. And this thing is equal to 0 because you have negative 31 divided by negative infinity. That's going to approach 0. So we have a negative infinity times a negative 21, which is going to give you a positive infinity. So the trick here, once again, is to factor out the biggest factor of x and then go from there. Now, when we have a numerator and denominator, it makes it a little bit easier. We don't actually have to factor anything out, because let's say we have something like this. Let's say we have like x plus 4 over 6. And let's say we multiplied both the numerator and denominator by 4. We're not changing anything, right? Because 4 divided by 4 is 1. So if you multiply by the same term or you divide by the same term, it's like multiplying or dividing by 1. And we're going to use that principle here. Because we have a fraction, which we didn't in the first case, which is why we had to factor out the x cubed and leave it there. But when you have a fraction, as long as we multiply or divide each term by the same thing, then we essentially divide it by or multiply by 1, so it doesn't change anything. So what we're going to do here is, when you have a fraction, we can divide each term of the numerator and denominator by the highest power of x. Like in this case, the highest power of x is x squared. So we're going to divide every single term by an x squared. Okay, let's see what happens. If you have 2x over x squared, we can simplify that. X and x squared simplifies to just an x on the denominator. 8 over x squared is 8 over x squared. And then here the x squareds cross out, so we have 8. X over x squared, there's one x left on the bottom, and we have a 6 over x squared. Now imagine you're plugging in infinity. So infinity is a concept, so imagine you're plugging in a very, very big number, like 50 trillion to x. 2 divided by a really big number is going to be 0. 8 divided by a really big number is going to be 0. So all these are going to be 0 because we have a constant and we're dividing it by x as x approaches infinity. So we basically have 0 plus 0, which is going to be 0 over 8, and that'll be 0. Same thing for this second problem. The highest power of x is an x cubed, so we're going to divide these each by x cubed. And if you simplify that, the x cubes cross out, so we have 8. X squared over x cubed is going to be 8 over x. X over x cubed, it's going to be 3 over x squared. Here we have 11 over x cubed. Then you have x and x cubed, so you have 9 over x squared, and the x cubes cross out, so we have a 7. Now all these x's we're going to replace with infinity. So this is 0, this is 0, this is 0, this is 0, and we're left with 8 over negative 7, which is just negative 8 over 7. Same thing in this last one. We're going to divide everything by an x squared, which is the highest power of x. So the first term, we have x squared over x squared, that's going to be 8. X over x squared, you have 2 on bottom, 1 on top, so you have 1 left on the bottom, 9 over x, and we have 8 over x squared. Here we have x over x squared, which is 11 over x, and we have 2 over x squared. If you replace all the x's with infinity, or a really, really big number that we know is close to infinity, then all of them are going to be zeros, and we have 8 over 0. 8 over 0 is undefined, which is going to be infinity. Okay, and the reason for that is because, remember, these are approaching 0. So if you take 8 and you divide it by like a really, 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 really small number, then it's going to give you a really big number. So as this approaches 0, 8 over that is going to approach infinity. So in this case, the limit is infinity, or in other words, it does not exist. If you want a shortcut, if the degree of the numerator is less than the degree of the denominator, then the limit is going to be 0. So for example, if I have the limit of f of x as, like, let's say you have x plus 4 over x squared minus 6x plus 1, where the denominator is bigger than the numerator, the highest power, then that'll be 0. If the degree of the denominator is equal to the degree of the numerator, then the limit is going to be the ratio of the leading coefficients. Leading coefficients are just the coefficients of the highest degree. So for example, let's say I have limit of f of x as x approaches infinity. And let's say my term is like 6x squared plus 5x plus 7 divided by 7x squared plus x minus 4. Then the limit is simply going to be the ratio of the leading coefficients. So 6 and 7, that'll be our limit. Now you don't have to use a shortcut if you like the other way better, like we've been doing here, where you divide by the highest power. Use that, whatever is easier for you. And if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. In other words, it's going to be infinity, so it doesn't exist. So for example, let's say we have f of x equals to x cubed, x cubed, not x squared. Let's say it's x cubed plus 5 divided by x squared minus 4x plus 1. The degree of the numerator is greater than that of the denominator, so the limit is going to be infinity, which means the limit does not exist. So again, you don't have to use this, but if you want to use a shortcut, you can. All right, now lastly, remember that if you have radical x squared, you always get a positive value. I'll give you an example. Let's say that x was equal to 6. So then radical x squared is going to equal to radical 6 squared, which is radical 36, and that just equals to 6. So x is 6, and radical x squared is 6. So in this case, if x is greater than 0, then radical x squared just equals to x. But what if x was negative 6? Okay, then we have radical x squared. This is going to equal to radical negative 6 to the second power. Negative squared is a positive because you have a negative times a negative. So this gives you a radical 36, which is just equal to 6. But here we can't say that this is equal to x because remember x is negative 6. But a radical is always going to be positive. So if x is less than 0, then the radical x squared is not going to be x because x is negative 6 and we can't have a negative radical. So it's going to be negative 6, which is positive 6. So if x is less than 0, then radical x squared will equal to negative x, because if x is negative 6, it'll be negative 6 or positive 6. Okay, so we want to evaluate the following limit, and in this case, the highest term is an x squared, but be careful because it's not just an x squared, the x squared is instead of a radical. So on the numerator, we just divide everything by x squared, right? Because it's in the radical. But the denominator is not in the radical. So radical x squared is going to equal to x. So we're going to divide these by x because we have a radical x squared, which is x. So let's simplify this. On the numerator, we have a radical 9 over x squared plus 2 because the x squareds cross out. On the denominator, we have a 9 over x, and then here the x's cross out, so we have just a regular 3. And then we are going to replace x with infinity. So here you have 9 over x squared, which is going to be 0 because you're taking 9 divided by a really big number. Here we also have 0, so our answer is going to be radical 2 over 3. Now, if you want to find the limit of this as x approaches negative infinity, we're going to have to use this following rule, that radical x squared is negative x if x is less than 0. And because we're approaching x as x approaches negative infinity, all the values of x are going to be negative. So when you have this radical, we're going to actually use a negative x. So same thing, we're going to divide everything by an x squared. However, because now the values of x are negative, we're going to use this second rule and put a negative at the front. And the same thing happens. You have a negative radical 9 over x squared plus 2 over 9 over x plus 3, same thing as before. These are going to be zeros, so the only difference is that instead of a positive, we get a negative radical 2 over 3, which kind of makes sense, right? If x is going to be positive, we have a positive radical 2 over 3, and if x is negative, then we have a negative radical 2 over 3. Then lastly, the line y equals L is a horizontal asymptote, which is a horizontal line that the function approaches but never actually touches at infinity and negative infinity. So whatever the limit as x approaches infinity of f of x, that is going to be the horizontal asymptote. Like in this case, we want to know what the horizontal asymptote is. So we divide each of these terms by the highest power of x, which is going to be x cubed. And then we're going to simplify it. So we have x over x cubed is x squared, and you have 18 over x cubed. X cubed over x cubed is 1. X over x cubed is x squared, and you have 5 over x cubed. Now, when you replace the x's with infinity, these are going to be 0, 0, 0, 0. So we have 0 minus 0, which is 0 over 1, and that'll be 0. So by the definition, y equals to 0 is the horizontal asymptote, because the horizontal asymptote is the limit as x approaches infinity of any given function. And that's it.